Welcome to this talk on machine learning security, specifically going deeper with adversarial samples. I want to start by saying thank you to the people that helped me to get this knowledge and improve my life. Kunal, Alireza, Rafe, Laurent, Jay, you guys are awesome. Thank you. So this is what we're going to cover today. A lot of people have been talking about adversarial samples in relation to deep learning. Today, we're going to actually show you that it's a lot more broad than deep learning. It actually affects almost every single model out there, if not all of them. So what are adversarial samples? Well, think of a machine learning model that takes images as input, and on its output, it tells you what it thinks the image is of. And it gives you a certain percentage confidence. So on the left, we have a picture of a cat. And when we run it through the model, if we don't mess with the image, it's going to produce an output like tabby cat, and it's going to give her a percentage that's pretty confident. Now, if we embed an adversarial perturbation, and that's humanly indiscernible. If you look at the right image, that image has the perturbation in it. When you run that through the model, it gets 99% confident that the picture's of guacamole. So what this talks about today is why that occurs and in different models. So let's take a look at this picture here. Now, this is a very simplified picture of a decision boundary. In that cat picture before, there could be tens of thousands, if not millions of decision boundaries, because each pixel is an input, and that input represents a decision boundary in one of the dimensional spaces. Now, when we look at this picture, these C's are your training data for the machine learning model. And the green area is the boundary for cat that the machine learning model learned by looking at all of the different images of cats that you gave it. You know, some of them are red cats, some of them are black cats, some of them are white cats, some are orange and gray. And they're going to, what the machine learning model tries to do is you tell it, hey, this is a cat. So what it does is it looks at all the features that you've given it, and it tries to group all these cats together in this high dimensional space. And then it creates the boundaries in between the different classes. Like here, we're just looking at the boundary between cat and the picture of guacamole. Now, the thing is, there are many machine learning models with thousands of classes. So you could have cat, dog, bird, plane, boat, car, guacamole. The thing is, we're going to simplify this picture because we want to understand things on a fundamental level. And what this red line is basically the decision boundary between what a human would discern as a cat or guacamole. And notice this red line crosses over both the blue and the green areas, meaning that our machine learning model didn't learn the correct decision boundary for separating these two classes. Now, it's normal. You know, your training data is going to, depending on what your model has, going to learn good or bad decision boundaries based upon the training data you give it. Now, let me ask you this question. Oh, and then the other thing is the boundaries. The boundaries are pretty harsh. So for example, when we train a picture of a cat and we give it to the model, we say, this is 100% cat and 0 everything else out. And so what happens is a cat and a dog might share certain features, pointy ears, like a German Shepherd, and cats have pointy ears, and they have fur. But the thing is, we're telling the model, wait a second, there's no similarity between these things. It's either a cat or it's a dog. And you need to find out what are the features that are distinctly different between a cat and a dog. And guess what? there's no gray area. It's not like we're going to say, well, this picture is a 80% a cat and 10% a dog, or this German Shepherd is 90% dog and 10% a cat because it's got the fur and the pointy ears. We're not doing that. They're saying everything has to be a 1 or a 0. So what that means is these boundaries are very sharp, and if you push something across them, they quickly become high confidence predictions. So let me ask you this. If you look at this red boundary, what area is what a human would say is a cat in relation to the red line? And what area in relation to this red line is what a human would say is guacamole? Well, if you said the area above the line is going to be categorized as a cat, so this would be pictures of cats, and that a human would see them as cats, even if they're perturbed, like that picture we had in the beginning. They're going to see it as a cat. Now, the thing is, the model, though, is going to have these blue areas, right? So we're going to have a situation where we have things that look like cats, but they're going to be categorized as guacamole. And so, in general, we can push a cat to a blue area to be guacamole. We can push guacamole into a green area and say it's cat. And even though it hasn't changed its overall look, the machine learning model, because we crossed the boundary, is going to say it's the other thing. And that's the general idea with adversarial samples. So what we're doing is, let's say we have a new input image of a cat, or guacamole, and what we want to do is we want to create an adversarial perturbation on this that's going to push it into the next class. Now, because there are millions of dimensions, there's a pretty strong likelihood that you pick any arbitrary image and it's going to be on the border with whatever target class you want to push this image to, because there's millions of them and they go in all kind of crazy places and locations. And so what you're going to do is you're going to find those inputs that are going to push the machine learning model to classify this as your target class. So here we're saying we want cat to be, a picture of a cat to be categorized as guacamole, or we want a picture of guacamole to be categorized as cat by the model. And so that's what we're doing. We're just pushing it across these boundaries, but we're not pushing it across the human boundary, right? This red line that's going to separate what a human is going to discern and distinguish between visible features that are what represents a cat, and visible features of what represents guacamole. So we don't want to push the images across them, because then they're going to physically look like the other thing, and that's not what you want. You want something that looks like the original, but is categorized radically different than what it should be. So when we look at adversarial samples, we ask, well, what can you attack? What types of models? And if you look at this, it's pretty much everything. And this is specifically related to deep learning. But today we're going to actually talk about the other machine learning models that are also prevalent in your enterprises and used within your enterprises to make decisions and to make predictions. And they're vulnerable as well. It's not just deep learning. Almost every single machine learning model has this vulnerability in it. It's almost like basically saying every single web app that you write has got a big parameter tampering or cross-site scripting vulnerability inside of it, no matter what you do. So when we look at the causes or the theories of why adversarial samples exist, there's kind of 4 prevalent ideas. There's insufficient data, which I'm going to show you examples of as we move forward, where if you don't have the right data, your model is going to learn incorrect decision boundaries. We also have non-robust features. So this goes back to basically how when you tell the model that something is 100% this and 0% everything else, and that's all you're doing, that's what they call the loss function, and you're telling it that, then the model has got to figure out from these images of cats and guacamoles what specific feature in these images are distinct from each other. And because the models typically work on what they call filters that are sized 3 by 3 pixels or 5 by 5 pixels, in extreme cases 7 by 7, you're looking at very small portions of an image. Even though they get scaled down through max pooling, you're still looking at pretty small patches of the image to try to find features that distinguish one class from another distinctly. And what happens is you may learn non-robust features that then are imperceptible to a human and can be embedded in other images and fool the machine learning models to look at those non-robust features and categorize them as the incorrect class. We talked about harsh boundaries and how you can just push something across a machine learning boundary and it will suddenly be 99% confident. And then we talked about high dimensionality, which means that there are millions of potential input values to tweak. And because of the million input features, we have a million set of these boundaries in between our classes that we can look for opportunities to take advantage of. So when we talk about the goal and intuition of adversarial samples, the goal is to get the model to produce outputs that are contrary to what a human would decide or would interpret them to be. Now, this idea also can be used when we look at models that predict if a certain text is spam or not spam. So we can basically try to get a model to categorize something as not spam when it was spam. And when we think about the intuition behind this, our machine learning models learn imperfect boundaries that vary from human boundaries. So we want to push the inputs across the imperfectly learned machine learning boundaries between classes, but not across the human boundaries, and then get a result where the picture looks the same to a human, but when it's fed through the model, it's going to return a radically different result than what's expected. So there's an overall attacking procedure when you're creating adversarial samples. It doesn't matter if you're creating adversarial samples for neural networks or for other classic machine learning models. You first need to understand the model's weaknesses and how the model works. And here, it's going to be important to understand the math if you want to do something creative, if you want to come up with a creative attack on these models. If you don't understand the math and how the models work intimately, then what's going to happen is you're going to be stuck to whatever limitations or capabilities that the tools that I'm going to show you and mention later have. The next step is to create a model with training data similar to the model that you're attacking. And what you're going to find is that the models, if you have a large enough sample of data in doing the same type of thing, are going to learn very similar features. And you can even supplement your model's training data by actually feeding inputs and looking at the outputs on the victim model to fine-tune your model. Once you have a cloned model, you can create adversarial samples with white box techniques and they will transfer because both models have learned the same or similar decision boundaries from the training data. So let's talk about Kang. This is the most basic machine learning model. And what its premise is that things that are close together should be classified the same. And when we say K, K is a number that will determine how many of your closest neighbors you're going to use to classify the thing you're trying to classify. So if we look at the bottom left here, we have red triangles, we have blue squares. And those represent the two different classes. That could be sick or healthy, it could be cancer, no cancer, it could be fit, unfit, it could be spam, not spam, right? And so the training points are these red and blue points, but the green point is the new point that we're trying to figure out what should this be classified as, spam or not spam. And here, what if K equals 1, we're going to look at the nearest point, training point, to that point that we're trying to classify. And that happens to be a blue square. And so what we're going to say is that if we use K equals 1, we're going to say this green point should be classified in the blue squares class. Now K can vary. The larger K will smooth out boundaries. And so, you know, companies will experiment with different values of K, larger and smaller, to get the level of accuracy they're looking for, but that presents opportunities. And so here, if we look at K equals 3, well, now this green point has flip-flopped its classification because out of the 3 points, 2 are the red triangle. So now, because of majority vote, the 2 red triangles are going to outvote the 1 blue square, and now this green point is going to be classified as a red triangle or class 2 point. Now, if you look at the right here, we have a situation. And remember that these are in 2 dimensions, so it's highly simplified. Whereas in the real world, you're going to deal with hundreds, thousands, or millions of dimensions and features. So right now, this plot example is only looking at 2 features. And what we're looking at is 2 features in 2 classes, the gold class or the blue class. And so the one thing I want you to notice and think about is right now, this is K equals 1. But what happens when K increases? What's going to happen to the points that are the peninsula or the islands is that they're going to change their classification. So let's take a look at this point. If we say that K equals 5, well then now the 3 blue points and these 2 yellow points, the blue points are going to outnumber the yellow points, and so this point and this point are going to be incorrectly classified as the blue class when they're the yellow class. Now, what you got to realize is that in a high dimensional space, when you just look at 2 dimensions in isolation, the high dimensional space is going to have these places where it juts out into another dimension, or it sticks a peninsula into another dimension. And so these will occur, and they'll be the correct label. But the thing is, when we change our K value, it's going to change how we classify these points. And so when you're attacking KNN, that's what you're looking for, you know, to change something from spam to not spam, is you're going to train your model and find these places where you have the peninsulas and the islands, and then you're going to try to craft your message such that it's going to be around these islands, and then hope that they're using a K big enough that's going to allow you to change the classification. Now, there are 2 papers here that go into specific detail on different techniques that you can use. And if you're interested, I would read those papers. But the next model we're looking at something called naive Bayes, and it's based on Bayes' theorem. And what this is doing is this means what's the probability of a given label, of a label given a set of input features. Now, typically you're going to have your data set that looks like this table up at the top. And what you can do is use Bayes' theorem to actually figure out this probability in the case of the probability of spam given these words and the probability of not spam given the same words. And whichever is higher is going to be the prediction of the model. Now, the way we calculate these conditional probabilities is we can flip-flop this here such that we're looking for the probability of these input features given the label spam. And then we just basically, like, let's say the 3 words in our input are Viagra, hurry, and limited. Well, those 3 words will be a combined conditional probability, but what we can do is with naive Bayes, if we assume that each of these input features are independent, then we can actually say that the combined probability is equal to the multiplication of the individual conditional probabilities. So here, that's what we're doing. So we have, given it spam, what's the probability that the word Viagra appears? And so we look at all the rows that are spam, and then we look for how many times out of all those rows Viagra appears, and that's our probability. We do the same thing here. We look at all the rows that are spam, and we say how many times did hurry show up? What percentage? And we do this on, and then we also calculate the probability of spam by just looking at all the rows and saying how many were spam, how many were not, and we get a probability and multiply those all together, and then we get a final probability. And here I just put in sample values. They aren't tied to this table, but which one do you think this model is predicting? Well, because this one's higher, then it's saying, given the words Viagra, hurry, and limited, it's a 90 or 89% probability that this is spam. Now, when you're trying to attack naive Bayes, what you want to do is you want to pick words that are in not spam that aren't in spam. And you want to put those in your text to then push this probability higher and this probability lower. So that's how you attack naive Bayes. When we're looking at linear classifiers, what we have is we have a line or hyperplane that we're trying to separate 2 classes. And the way we define this line generically is up here, and is this formula here. And what we do is we learn these W values. And in this particular case, the W values are -1 and 1. And we have a bias, which allows this line to shift up and down on the y-axis with 0 because it goes right through the origin. If this bias was 2, well, this line would go through 2 and it would go this way, right? So the way that a linear classifier works is you're going to take the points that you want to classify, like this point here, 2, 2, you're going to plug it in, and sorry, this is x equals -2, y equals 2. So -2 times -1 is a +2 plus +2 plus 1. So that's a 4. Because it's a positive number that's come out of this, when we plug in our values, we're going to say this point is in the positive class. When we take this point here, we're saying x equals 3 and 1. So if it's 3, it's 3 times -1 is -3. 1 minus -1 plus -3 is -2. So we're going to say now, because the output is negative, we're going to say this is in the negative class. Now, when you look at this, when you're thinking about adversarially and attacking it, what happens if our training data was missing a lot of valid training points? So if you look at these light blue stars, they're associated with training data in the positive class. And we look at the light red or pink stars, they're missing training data in the negative class. Now, if you had this training data, then the real boundary is here. But because we didn't have that training data, we learned a boundary like this. So what does that mean about our overall technique that we're going to use to create adversarial samples? Where do we want to start images with that we're going to be able to push them to another across the incorrectly learned boundary, but not across the human boundary, right? So if you think about that. Where are we going to push, points that are on this side of the line, and where are we going to push points on this side of this incorrect boundary to get adversarial samples, which basically look the same. This is our human discernment. Human look the same, but are categorized differently by the model because we've crossed the machine learning learned decision boundary. Well, those points, right? So once we push one of these blue points across here, but not across this, now because we push it across the machine learned boundary, it's going to be reported as belonging to the negative class when it's really a positive class. And it's going to look like a positive class because it hasn't crossed the human boundary. And the same thing goes for this location. I'm going to push these negative class points across the decision boundary to points that are on the other side of the incorrectly learned machine boundary, but we're going to make sure that we keep them on the same side of the human boundary. And if you're looking for examples, I have links down there where you can actually try this out. And they have notebooks for you to do this. The IBM Adversarial Robustness Toolkit has a bunch of nice attacks and defenses that you can experiment with. Let's talk about decision trees. So with decision trees, you have all of your training data and you're trying to find which features and which values in those features will serve as good split points to result in child nodes with the highest purity or the lowest impurity. And what you want to do is you want to start and find that split point and that feature that's going to give you the highest split and the highest purity of children. And then you're going to keep on splitting until all of the leaf nodes have one label or all of the same label, or the leaf nodes have a certain number of nodes in them, and then you can take a majority vote or an average of the results, depending on if it's a regression tree or a classification tree. But the important thing to understand about how these models work is that because you're dealing with that subset of the data, your decision tree is going to learn jagged boundaries around that data. When you make these decisions to cut left or right, or where to split the group, that's what's happening. And if you notice here, this yellow line is the decision boundary for what a human would discern between everything that was blue in the blue class and everything that was in the red class. But what's learned by the model is this boundary here between the red and the blue classes. And if you look at this, you can see that there are a lot of opportunities to cause misclassification where you don't change what's humanly discernible, but you change the features and the model change its prediction. So if I were to say, where would you change a red point to a blue point, but not make it look different to a human, or a blue point to a red point, but not make it look different, not change its blueness or whatever its characteristic or label, but you're going to change the model's results, where would you be looking at this decision tree? On what boundary positions? It's basically all the points that are sticking out, right? Those are going to be where you can push blue into a red boundary, not change what it looks like to a human or what it's perceived as by human, but the machine learning model will suddenly make a different result, will make a different prediction, an incorrect prediction. And if you want to look at different attacks, I have a link here that you can go to, and they have a notebook, and you can try it out yourself. When we look at random forests, basically we have a situation like decision trees where it's a collection of decision trees, but each decision tree is sampled or created with training data sampled from the original training data set with replacement. And at each decision split point, we're only looking at a subset of the features to split on. And so, and we keep on doing this over and over again till we have a lot of decision trees and we average the results or take a majority vote of the decision trees. The individual decision trees are created using this technique. And if you look, you compare the boundary from what a decision tree learns, there are a lot less opportunities and it's a lot tighter. However, there's still opportunities, right? Where the places jut out from across the human boundary and where there's a mismatch, those are opportunities for adversarial samples. So what we have here is another example of something you can look at to experiment with. When you look at support vector machines, basically what we're doing here is we're trying to maximize the difference between the closest point to the boundary line, the machine learned boundary line. And we have this formula here that we use, which is our objective and our constraints. And the same thing can occur with linear support vector machines. So if your training data is bad, well, the support vector machine is going to learn a incorrect boundary. And as we've been talking about, once there's an incorrect boundary and it's mismatched with the human boundary, it's going to give you an opportunity to create adversarial samples that do not look different to a human, but have drastically changed the output prediction of the model. And again, there's an example here in the links on this slide. So when we talk about adversarial attacks on neural networks, there are many ways to do this, and I talk about this in my other talks on adversarial samples. I wanted to do something different to let you know how expansive this problem is, and that it's not just a problem related to deep learning and neural networks. It has the same process, but basically you're going to clone the model, but the thing is here you're taking partial derivatives of output class with respect to the inputs, because neural network models typically differentiable. There might be some difficulties if you're using dropout, but you can predict what the gradient values are that you need to modify. But in general, what you want to do is you want to take these partial derivatives to find out which inputs are going to push you in the direction of your target class. And then once you've found the adversarial samples on your cloned model, they transfer it, meaning they work on another model that's been similarly trained to solve a similar problem or the same problem, and which has learned the same features because you've used a sufficiently large enough data set to learn the appropriate features that are going to lead to decision boundaries that are shared between your cloned model and the victim model that you're attacking. Now, when we talk about defenses, the two most prominent that have come up recently are adversarial training and removing non-robust features. Adversarial training means that you take your training data and you embed the adversarial perturbations by using these frameworks and toolkits like the ART from IBM and Clever Hans and some of these other toolkits to embed these perturbations in your pictures, like the cat, the guacamole perturbation. And what you do is then you label the previously incorrected image as the correct label, and you basically train the model to say, hey, this feature that was guacamole is not really guacamole. And so you're trying to remove those features. The downside is that because you're now taking these images and your training data and essentially duplicating them, but just adding perturbations inside of those images, you're overfitting or you're overtraining on your training set. And so it could result in training data set leakage. And in addition to that, you're going to take a hit in terms of accuracy, because these features that were found were kind of strong indicators, although they weren't visible to us, they were visible to the machine learning model to distinguish between all the different classes. So if you want to experiment, I suggest you take a look at Clever Hans, IBM's Adversarial Robustness Toolkit, Toolbox, and then many others. And the link is actually on the many others, there's a link to a page that has the other tools that you can use. So in retrospect, this leads to a question about why adversarial samples are so prevalent. And what it's saying is that basically the machine learning models are learning features that may be important to distinguishing between these classes, but that are not the features that we use. And in some cases, this is going to be good, and in some cases, it's going to be bad. So for example, if you're looking at, images, radiological images of, tumors or people's brains or blood vessels, you want the machine learning model to use its microscopic vision to basically identify things that a human would not be able to see, and thus give you early signs or early detection of these things. And that would be good. However, when you have a cat it's categorized as guacamole, it's not a good thing, because you can see if an attacker can use this to basically get a tank categorized as a bus or whatever, then you're going to have issues in the field. And so what we have to do is we have to understand that if adversarials are very prevalent, it means that there's something fundamentally wrong with how machine learning models are learning to distinguish between different classes and what we're doing. And we need to find a way to help the machine learning models to distinguish properly. And in certain cases, like the radiological example, you may want the current setup. So if you have any questions, please contact me or Kunal. Kunal is the other person that usually does this talk with me, but he was not able to do this, and I'm going to open it up to questions.